Hi, everyone. Good morning, good afternoon, and good evening to you from wherever you are joining. And today we'll be talking about the difference between eventing and streaming and how you can combine them to build reliable and scalable messaging systems. I'm Dhanushka, a senior developer advocate from Redpanda Data. For those who are new, Redpanda is a streaming data platform, API compatible with Apache Kafka. So I come from a background in streaming data, stream processing, and real-time analytics. So I use I share my experience throughout blogging and speaking at conferences like this. So hope you will enjoy the session. All right, let's get started. So eventing and streaming. So they are both popular patterns in the messaging domain. So although they look familiar, similar in outside, they have differences in their behavior. So the goal of this session is to help you understand their differences in detail. So we'll take a deep dive into their differences and we'll compare and contrast their differences with real world scenarios. And then we'll also go through a couple of use cases catered to different use patterns. And then finally, we'll look at a couple of solutions that we can build by combining both eventing and streaming using Solace PubSub and Redpanda as a production alternatives. Right, let's get started then. All right, before getting going any further into eventing and streaming, uh, for us it's important to understand the fundamentals. So let's go to events. So, what do you know by events? So, an event describes something that happened in the past. So, events always ends with the past tense. So, for example, we can take a couple of real world examples like an order has been placed in our e-commerce system. A sensor just captured a temperature measurement. And then, for example, we can take a couple of other real world scenarios like uh, an email has been sent, alarm has been triggered. So there are so many. The list goes on. So when you look at a individual event, each event carries a collection of facts. So these facts will help you understand what really happened. For example, this could be the timestamp where the actual event happens, and then comes the payload. So this payload contains different attributes related to the event. For example, if we take the sensor measurement, sensor reading, this could be a fact could be a sensor ID. Another one could be the current temperature measured. So, so that's how it works. And most important thing is these events are immutable. That means once happens, this you cannot change these facts. So that's why they are called immutable, and they are not. You cannot change them in transit or while in transit or while they are stored in some sort of a medium, storage medium. When we consider an event-driven architecture, events form the backbone of these kind of systems. When we look at a typical event-driven system, we can identify three significant components: producers of events, event broker, and event consumers. So event producers are the systems that produce events to signal to others or the other outside that, oh, hey, there's a state change happened inside me. So this is the information. So that's how uh, events are emitted from this. So basically, it's called publishing of events, and these events are published towards a topic in the event broker. So this topic is actually an abstraction in the space. So here, the job of the event broker is to decouple these event producers and consumers so that they don't know each other, so that they can scale and version and evolve independently of each other. And on the other hand, we have event consumers who are interested in reacting to these events. And what they usually do is they subscribe to these topics and then they receive events and then they react upon those events. So those are all business scenarios. For example, we can get a real world scenario like and a customer in a CRM system has changed his recent address. And then the producer, the CRM system generates an event and places that in a topic. And then on the other hand, from the consumer side, we have the shipping service or shipping system. So what usually it does is it listens to these events and updates its uh, internal details. So, having said that, when we talk about eventing and streaming at a very high level, we can say that eventing is a pattern of reacting to discrete events without considering their past behaviors. So, in a typical eventing system, or a consumer, as we can see in the a couple of slides later. So, these systems react to events in isolation, and there's no memory of past events. Whereas in streaming is a pattern of reacting to a continuous, unbounded stream of events. So that's stateful way of processing events. So we'll understand their differences as we go through the presentation. All right, now let's talk about their differences. Like I mentioned in the beginning, although streaming and eventing they look familiar and similar in outside world, they have differences built into them. So the closest real world analogy we can take from the outside world is alligators versus crocodiles. They may look similar, but they have different characteristics. So do streaming and eventing as well. So let's compare and contrast streaming and eventing across a couple of dimensions. So the first dimension is the event delivery semantics. That means how a consumer would receive an event from the broker. And so that's the first difference. In eventing, generally, events are pushed out from the broker to all consumers. So the typical workflow starts by consumer register or subscribe to a topic in the event broker. And then whenever an event comes, event broker iterates through all the subscribers of that particular topic and push out that message to those consumers. So that's the push-based delivery semantic. In contrast to eventing, in streaming, it's rather a poll-based or pull-based event reception. That means the consumer has to poll the event broker for new messages. So the typical workflow begins by like similar to eventing. So the consumer has to subscribe to a particular topic in the event broker, and then it has to wait. It has to keep polling until new messages come. If you are familiar with this Apache Kafka and related streaming data platform, this happens through sending a fetch request to the event broker. So in this fetch request, it contains the start offset. So this is something like a cursor. So uh, for example, a consumer can ask for latest messages in the event broker by sending a fetch request to, let's say, last 100 message events from the broker. And then uh, event broker reads this fetch request and responds with all the messages starting from that offset to the end of the most recent end of the message event collection. Next difference is how the processing style. That means how do they react to events coming from the broker, especially consumers. So in eventing, uh, consumers react to events in isolation. That means they treat discrete events and trigger their business logics. And there's no past, there's no correlation with past behavior or aggregated output of the incoming events. So all the events are considered as isolated and discrete incidents. Whereas in streaming, it's a different story. In streaming, as you say, as we discussed earlier, um, consumer has to fetch record all the events from certain place. So this is done by sending a fetch request to the broker, and then consumers typically get all the records from the broker. So if the producer is continuously producing data, consumer will receive a stream of events. So this stream will have no beginning or end. So the consumers has to process them continuously in order to generate an output. So these kind of consumers, we call them stream processors, and they have different semantics to deal with this kind of streaming messages, events. So for example, let's say uh, anomaly detection system. So when this kind of stream, let's say temperatures readings are coming as reading events, and then the consumer has to process these events continuously. So since there's no beginning or end, so the consumer applies this windowing concept in stream processing. So in windowing, we can batch these incoming events to different batches, perhaps based on the time or based on the count. For example, we can group the last five messages or last five events together and apply certain transformation. Or we can take all the events that came in the last 5 seconds and do certain summation, aggregation, or something like that. So that's we call stream processing. So the idea is uh, in streaming, all events are treated as a whole aggregation, and there's no single event in isolation. And another most significant feature is the ability to support event filtering. So there's a significant difference in eventing where the events are filtered at the broker level. So, so whenever an event comes, so the typical workflow begins by consumer subscribing to a topic in the event broker, and upon subscribing, uh, the consumer can set a filter condition. So this filter condition means, say for example, uh, if the consumer is subscribing to receive stock alerts, probably it can set a filter condition saying that the symbol should be similar to something like foo or ba. And then when a new event comes to that particular topic, the event broker iterates through all the subscription and evaluates the event's payload and headers against all the filter predicates or conditions. Only the events that matches against the criteria or the filter conditions are pushed out to consumers. So this is a great advantage for consumers who lack in processing power, so that the filtering can be done at the broker level without getting worried about at the consumer level. Again, the streaming, there's no control for the consumer to filter out events at the broker level. So consumer has no choice but to read all the events from the broker and process it mostly through sending them through a stream processing system or writing a different programming logic. That's the main difference. And then another retention, another significant uh, difference is the retention. How long events can be retained or stored in a event broker. In eventing, events are considered transient. That means once an event has been pushed out to a consumer, the consumer has to acknowledge the broker by to say that the event has been received successfully. And then once receiving this acknowledgement, the broker no longer interested in keeping this event. So it deletes the event from the storage. So that's why they are called transient. So typical, that's the typical behavior, but certain event broker implementations are there. So they provide durable subscription. So even though the consumer is offline for a couple of minutes or hours, message can be persisted, but it's an special case in there. In streaming, these streaming data platforms like Apache Kafka, Redpanda, and Apache PubSub, they have been designed in long-term event retention in mind. By their architecture, all incoming events are appended to this distributed append only and immutable log files. And by default, they are kept in the local disk for like maybe weeks or days or maybe even hours based on the event's arrival rate and the processing throughput as well. So, so that's the major differentiator. Also, in streaming, there's this tiered storage new feature available. So, instead of keeping the events in the local storage, you can push out all the events into more reliable and more economical, cost-effective cloud storage buckets. So that way, you can minimize the total cost of ownership when operating streaming data solution at scale. All right, so those are the differences that we can see in between eventing and streaming. So let's talk about a couple of real-world use cases that caters to certain patterns. So what are the use cases for eventing? So when we try to understand the use cases, the principle you have to keep in mind is eventing is mostly about reacting to discrete events. So that means you consider and act upon events in isolation. So based on that principle, we can identify some patterns. Say, for example, we have event notification system. For example, instant messaging, email sending, writing to another topic. So there are certain ways. So this kind of event propagation is called fan out pattern. So it works like the producer send an event to a topic, and then there can be different subscribers subscribe to this event notification, like email client, instance message, or Slack client. So they all can read message and write to different subscribers. And then enterprise integration is another significant use case in this domain. So uh, especially events can be used to transfer state changes across different heterogeneous systems. Say, for example, like I said, um, a CRM system can publish an event of a customer changing his recent address. And then this event can propagate it to different systems. For example, again, this can be received by a warehouse microservice or something, and then it can react to this by changing its internal state. And then choreography. Events are instrumental in running these choreographies in microservices, especially when one microservice has to communicate state uh, changes across multiple different microservice instances. And then when it comes to streaming, all we have to think is streaming is about dealing with streams, aggregated events. That means streams of events. There's no beginning or end. That's not simple event processing. It's about stream processing. And reliability, accuracy, and scalability is a matter. And those are critical in stream processing. So that's why we use streaming for um, real-time analytics, use cases, anomaly detection, fraud detection, mostly IoT applications, stock trading like those, and then recommendation, real-time machine learning like those use cases. All right. Now the question is, can we combine both of them so that we can build more scalable and reliable and most importantly cost-efficient messaging systems in production? Can we, how this can be done? So, so, so we know, so as we discussed, eventing is better. So for certain kind of features, like we can leverage eventing for built-in event filtering. So the consumer doesn't has to worry about filtering out events at the consumer or code level. So it can be done at the broker level. And then this kind of eventing middleware can be used for routing and events to different destinations. So certain eventing systems have this routing capability and hierarchical topics, especially I think Solace PubSub Plus as well. So they have fine-grained authentication for different levels of topics. So by subscribing to different levels of this topic hierarchy, consumers can get different filtering of events, and they can get different treatments, different SLA levels as well. And then you can leverage streaming for long-term event retention and do it with more cost efficiency in mind, especially with leveraging this tiered storage facility attached to streaming data platforms. You can use more reliable and cost-efficient cloud storage buckets for long-term retention. And then especially strict ordering when you are especially when you are building this kind of financially and this kind of business critical application, and if the event ordering is really critical, you should consider streaming for that. And then uh, scalability and reliability, when there's a need, the streaming is the best answer for you. So how do you build such system by combining these things? What are the technical solutions we have in place? Well, speaking of Solace, so they have this Kafka uh, mesh or Kafka bridge. So you can uh, combine Solace PubSub Plus with Kafka. So generally, the perception is Kafka is deployed in on-premise, mostly in on-premise, and while PubSub Plus is available in the cloud. So this is a good use case for bridging these two gaps. So there are uh, Kafka source and Kafka sync connectors available in Kafka Connect. So you can leverage these two to bridge this gap. And speaking of Redpanda is a uh, drop-in replacement for Kafka. So that means if you have an already existing Kafka producer or consumer, you can seamlessly integrate that with Redpanda for processing large volume of events at higher throughputs. So Redpanda is a Kafka compatible streaming data platform. So and we already know that Solace PubSub Plus is a cloud-based platform, and it's good for, and it's better known for having support for multiple protocols, messaging protocols like IoT, MQTT, JMS, MQTT, and Stomp, and there are so many. And this so when you are designing a solution, this PubSub Plus can be put in the front end. So uh, PubSub Plus can collect different events coming from multiple protocols, and then we can uh, funnel these events through to Redpanda through relevant Kafka connector. So there can be Kafka sync connector. We can reuse Kafka connector because Redpanda is capable of inter compatible with Kafka as well. And then once the events land in Kafka, they can be scalably processed. So it can be funneled through different streaming ETL systems or stream processing and so on. So that way we can combine the best of both worlds to build a more reliable, scalable, and cost-efficient messaging system that scale. All right, so let's try to wrap up what we have discussed so far. Um, while so, like I mentioned in the beginning, so streaming and eventing are two popular patterns in messaging world, but they have different behaviors, but they both built upon the very foundation of event-driven architecture and events. Um, Especially when we talk about events, eventing promotes built-in event filtering, routing, and fine-grained authorization. And uh, it all boils down to in eventing, you can do process uh, isolated discrete events. Whereas in streaming, you process streams of unbounded data. That means it's real time. So uh, the consumers has to process the incoming data at a scalable and reliable manner. So the processing has to be continuous. So that's why we mentioned about stream processing systems, and especially when consumers has to apply streaming stream processing semantics like windowing, filtering, transformation, etc. And then when it comes to building and designing large-scale event-driven systems, you can combine the best of both features of them. So, for example, we talked about an example in Solace PubSub Plus and Redpanda. So you can use Solace for collecting events from different systems over a couple of multiple protocols, and then funneling them to Redpanda for scalable and reliable event processing, such as analytics, stream processing, and so on. All right. That's all I wanted to discuss with you today. Hope you understand the difference between these two patterns and hope this knowledge will help you design, build, and operate large scale event driven systems in the future. So, if you have any questions, feel free to reach out to me in Twitter. My Twitter handle is DunitD, and you can find me in LinkedIn, and you can find my writings on Medium as well. If you want to check out more information of Red Panda, feel free to visit redpanda.com and check out the documentation and the blog as well.